Hello, this is Mr. Huff, and this is a real quick overview of gears, pulleys, and sprockets for the engineering class, Principles of Engineering. Okay, I'm just going to go through the PowerPoint here and kind of bring out some things. So really, when we talk about gears, pulleys, and sprockets, these are things that transfer energy and turn it into rotational motion. So we're taking some form of energy and we're making it spin. And the things that we can control when we are talking about things that spin, we can control the speed at which they spin, we can control the direction, clockwise or counterclockwise, and we can change the amount of torque, which is torque is what makes work happen in rotating systems. This is just showing that the teeth have to interlock. So you can see that for the teeth to interlock, they have to be the same size, shape, and pitch, or they won't match. They have to match so that they can turn one another. And we have a train when two or more gears are connected. And the driver gear causes motion. I want you in your notes to note that the driver is input. So this is the in part of the gear. And then the motion is transferred to the driven gear, so that is the output. So if we turned the gray gear here and it was turning the yellow gear here, the gray gear would be the input and the yellow gear would be the output. Whenever you have two gears that are contacting each other and they're turning, they always turn in opposite directions. You can see in this case the blue gear turns in a clockwise direction and the red gear turns in a counterclockwise direction. Did I say that wrong? No, that's right. It's turning a counterclockwise direction. Another thing to note is that if you put an idler gear between two gears, all that does is it changes the direction. If the first and last gear are the same size, they will go to the same speed, but they will also go in the same direction because of the idler gear reversing that direction in the middle. And we have already talked about how gears have to have the same size teeth. This first statement is easier to understand. The larger gear always moves slower than the smaller gear. So let's look at the blue gear and the red gear in this example. So here we have the blue gear is turning slower and the red gear turns faster because of the greater number of teeth or the larger diameter. So we'll get into the formulas in just a moment. And if you have two gears that share the same axle, like this yellow and blue gear here, these two are on the same axle. That means they spin with the same speed. They have the same revolutions per minute. Okay? So here are the variables we will use for gears, pulleys, and sprockets. N represents the number of teeth, and it's just a count. There is no unit for the number of teeth. D is a diameter. It needs to be in inches or meters or centimeters. As long as you are consistent with your measurements, it won't make a difference as far as the ratio. And this is the Greek letter omega. This is a lowercase omega. It looks exactly like a butt, so we will refer to this as the butt equations when we see that. But it's a lowercase omega if you want to be technically accurate. And we are going to be using RPM to describe angular velocity. In some of your physics classes, or maybe in your pre-calculus class, you may talk about radians per second. So it's just basically the number of degrees that something turns in a given amount of time. This is the Greek letter tau. It looks like a little T with a little curly Q at the end. And it represents torque, and we'll talk more about torque in just a moment. But right now, just think about torque as a twisting force. It's a force that causes rotation, okay? So it has it's a little more complicated than a force. It's not the same thing as a force, but it involves force. All right. Some equations to know. These are all equal to one another. They are ratios. So the ratio of the number of teeth on the output gear divided by the number of teeth in the input gear, that ratio is the same as the diameter of the output divided by the diameter of the input, which is also the same as the torque on the output divided by the torque of the input, which is also the same as the angular velocity, omega. This is the little butt thing. So this is omega in divided by omega out. The angular velocity in divided by angular velocity out. Note that angular velocity and torque are opposite of one another. If you increase the angular velocity, you decrease the torque. And conversely, if you increase and then it's the same way if you increase the or decrease the angular velocity, you increase the torque. So they trade off. If you increase one, the other one has to decrease. So in the book or in the presentation, it goes through an example, and it shows you how, if you do all the calculations, these all equal to a gear ratio of 2 to 1. So, and that assumes that the output gear is 12, so we're saying this is the output gear, and the little brown gear is the input gear. So the little gear is turning the big gear. All right. So I want to cut to the chase on this. This is a gear train that has 4 gears, and when you're calculating gear ratio on this, you don't have to calculate every connection here. You can shortcut this by looking at your first gear and your last gear and calculating the output diameter divided by the input diameter, or the output number of teeth divided by the input number of teeth. However you want to do that, you will find that this gear train has a because it's 20 teeth on this side and 20 teeth on D, that the ratio is 1 to 1. So, and it goes through this long complicated process of showing you how the different gear ratios, if you take the sum of all of those together, or the product of those, rather, they're multiplied, it's the same as taking the input gear and the output gear, and that's really all you have to do. Alright, that only works if they're in a straight line, not if they're compound. Okay, now this slide is interesting. It shows mechanical advantage and gear ratio and the things involved. There are a couple of things to point out. They are similar equations, mechanical advantage and gear ratio, and in a compound system you just multiply the mechanical advantages and you multiply the gear ratios together to find the total. But you need to keep in mind the last 2 lines are the most important on this slide. The mechanical advantage only applies to forces, not torques. And the gear ratio only applies to torques, not forces. You cannot interchange mechanical advantage and gear ratios. You have to handle those independently. They are describing different physical characteristics. So we're talking about forces versus torques. They are not the same thing. And then it goes through this terrible example of this compound machine where it has 2 levers and it has a gear ratio. So we have a wheel and axle. Well, actually it's a wheel and axle, a gear train, and a wheel and axle. So you have to handle those independently, find each one, the mechanical advantage for the first and third one, and then you can find the gear ratio for the what happens in the middle. And because we're talking about forces and torques, you can't mix those 2 up. So looking at the first one, they take the ideal mechanical advantage, which is the distance of the effort arm divided by the distance of the resistance arm, and they get a mechanical advantage of this first lever at 2.67. And then they move on to the gear ratio and they count the number of teeth, output over input. So you have 24 over 60. Did they do that right? Yeah, the output is 24, the input is 60, and you get a gear ratio of 0.4. And then they look at the second lever, or the second wheel and axle, and this mechanical advantage is calculated at 0.17. So for the mechanical advantage, you're going to multiply the 2.67 times 0.15 and you get about 0.4. And that's the mechanical advantage of these 2 levers working, or these 2 wheel and axles working together. The gear ratio is only the gear ratio between the pink and the blue, and it's also 0.4 because that's what we calculated. I hate that they're showing that the mechanical advantage is 0.4 and the gear ratio is 0.4 when they are independent things, so it's a little confusing. Alright, here is a compound gear train. I really love this animation. So you have the driver, or the input gear, and it is driving a yellow gear. Connected to the same shaft is the blue gear, and then connected to the blue gear would be the red gear. So you can see this little green gear is spinning like crazy, and the output gear is going around really slowly. And if you count this, this will go around 10 times while this goes around once. But we're not going to count that. We're just going to read what it has to say. So this is a situation where you have the gears on this are going the same speed. The yellow and the blue gear are turning at the same revolutions per minute. And we are going to have to multiply the gear ratio between the The red gear and the blue gear, we need to know the ratio there, and the yellow gear and the green gear, we need to know the ratio there, and then multiply those two together, okay? So you have to find the gear ratio between A and B, and they show you how to do that. It's 4 to 1. And then you have to do the gear ratio between C and D, and they do that, and it's 2.5. So to find this compound gear ratio altogether, you multiply 4 times 2.5, and you get a gear ratio of 10. And if you will review to what I remind yourself of what I just said, the green gear turns around 10 times for every 1 time the red gear turns around. So we're taking a high angular velocity and turning it into a low angular velocity, but a very high torque. Belts and pulleys is essentially the same equations as gears, except for we can't count the number of teeth because there are no teeth on a pulley. So we have to consider diameters, angular velocities, and torques. And then it goes through the calculations work exactly the same way. So it's really all about ratio. So if you know the ratios of these things, then you know the gear ratio. So really, technically it is a gear ratio, even though it's not a gear. Also keep in mind that the angular velocity and the torque are opposite one another. If you have a high angular velocity, you will have a low torque. If you have a low angular velocity, you will have a high torque. For the chain and sprocket system, it works just like the pulley, except now you have teeth to consider. So you can consider the number of teeth, the diameters, the angular velocities, or the torques to determine the gear ratios. So all you're doing is you're transferring the energy from a gear to another gear via a chain. Okay, so and they go through some calculations for you to show that the ratios remain the same. And that the units cancel. So it's truly a ratio, and these all have the same ratio. So that's sprockets and chains. The last little bit of this, let me turn on the laser pointer because I like it better. Okay, so right here, pulleys. The advantage is using a belt. It's quiet, you don't need lubrication, and it's inexpensive to make a belt. It's cheap to make a belt. You can make a really cheap belt. Problem is, pulleys can slip, like if they get wet or if they get polished, they can slip, and that's a problem. For sprockets, they're driven by a chain, and the advantage of that is it does not slip, and they are extremely strong. And we talked about timing chains in old cars versus timing belts in new cars, and kind of how the old cars, the chain was a lot better, but they tended to wear out. The new cars, the belt lasts a long time, but when it fails, your engine gets destroyed. So, and then the other problem with sprockets is it's a high cost. You have to run them with lubrication. If you've had a bicycle, then you know about keeping the chain lubricated. And they tend to be noisy. If you look at World War II movies where they show a tank going by, they always have the squeaky treads going by because that's just a big chain, and they make a lot of racket. So, okay, that is a rundown on the gears, pulleys, and sprockets. Basically, just all you need to know. These are notes you should have already taken, and that's all I have.